All right. Hello, all you track runners and cyclists out there. What? No, but the girls. Yeah, so are you guys not running track? No. I did not know that. Okay. So, but we've got cyclist and anyway. Okay. So 6 to 50, 56. Okay. So chapter 17, 50, whoa, where's this at? Okay, so 56 reads like this. It says, calculate the solubility in grams per liter of wait, what? This isn't 56?
It's above the question, the original question.
Okay, take two. Calculate the solubility of LaF3 in grams per liter. Oh, I get it. If you've got some additional KF added to the, okay, all right, I get you now. Okay, so we understand the idea that we got squiggly dude, right? Because that's undissolved, that's a solid. And then we don't have any lanthanum because that comes from the dissociation. But in this question, we have an initial concentration of fluoride ion, and that comes from the addition of probably sodium fluoride, potassium fluoride. Is that okay? Okay. So then, was that enough?
Yeah.
Really?
So, yeah.
Okay, so it really is just common ion effect. But guys, please hear this. On the AP test, one of the things that's going to be really tricky for you, especially in recent years, is figuring out when to grab your calculator. Because it used to be, up until about 4 years ago, you didn't have your calculator in the multiple choice. So you knew that everything in the multiple choice was going to be brain doable rather than this. So with that idea, and Joan, I know what you're saying, you're like, oh, now I get it. We got some fluoride coming from somewhere. Conceptually, you'll also see this. Hey, you've got a solution, got some lanthanum fluoride in it. If you put sodium fluoride or potassium fluoride in it, what happens to the solubility of the salt? So you guys, you understand what I'm saying? You also have to understand this conceptually in multiple choice. So the big idea here, and we could go up and look at A. So in A, we figured out the solubility of this, and it's on the order of 2 to the negative third grams per liter. So if we add additional fluoride, what will that do to the solubility of this? It makes it go down, because Le Chatelier's principle says if this goes up, it drives the equilibrium to the left, and the solubility will go down. And we can verify, oh, wow, right? It went down a lot. But you've got to be able to also eyeball that in multiple choice and go, wait, I don't, and they'll give you numbers. But they would give you something like this, and they would say, hey, this salt has a solubility of 1.8 grams per liter. What if you add sodium fluoride or potassium fluoride? And they'll give you numbers, but only one of them will be less. Do you know what I'm saying? So guys, you've got to be able to sort through this not only mathematically, but conceptually. What else, y'all? Yeah?
49B.
Oops. B? Oh. Yeah. Yeah, so here let's look at, so the tricky bit is this. Mercury has 2 different forms as an ion. The strange bit is they both have the same charge. Here, let me get in writing mode so that our friends overseas can see this. So the idea is that Mercury does 2 different things. You can have Hg, wait, they're both plus 2, right? Yeah, so we can go Hg plus 2, or we can go Hg2. I should do this right. Hg2, 2 plus, or Hg. Oh, I'm in eraser mode. There we go. So Hg2 plus or Hg2, 2 plus. So mercury's got two different forms as an ion. They both have a charge of 2 plus. The difference is this is one mercury atom with a charge of 2 plus. This is actually diatomic, but it also has a charge of 2 plus. So when it dissolves in water, when it ionizes, the Hg2 stays together. So it's obscure, but that's actually the case. So, what else, y'all? Good? Yes.
So I was just confused. Like I sort of got what's the difference between solubility and soluble product?
I don't. Well, I mean, we could talk about the words, but
It is
50?
50.
So here, let's just talk about it and see if we can get to the heart of this. So solubility, the term solubility, so we can talk about it qualitatively, and we can say, what is the solubility of this substance? And we can say insoluble, slightly soluble, or soluble. And really what we're talking about is strong electrolyte, weak electrolyte, and then something that doesn't dissolve, insoluble. So we can talk about it qualitatively in terms of solubility, but then we can also hang a number on it. And when we talk about solubility with a number hanging on it, we're then talking about, this is the way we chose to define it, how many grams of stuff will dissolve in 100 milliliters of water. Is that okay? So it's literally, I mean, we did it in that lab, right? When we did the heat of solution, and some of you guys found that you added so much salt that it wouldn't all dissolve. So you got over that cap of how many grams will dissolve in 100 milliliters. Then there's the solubility product. And the solubility product, remember product means multiply. The solubility product is the product of, for a slightly, well, it is slightly soluble salts. For a slightly soluble salt, the solubility product is the molarities at which the salt saturates multiplied together. Is that okay? So the difference mathematically is solubility is given in the units grams per 100 milliliters of water. KSP is the product of molarities, not grams per 100 milliliters, but molarities. But then remember, it's dimensionless. All of our K values don't have units. They're a dimensionless number, but they give us a sense of also how much will dissolve. Is that okay? And then we also talked about the relationship, and guys, this is important. We talked about the relationship between Q and KSP, and Q is KSP solved at non-equilibrium conditions, and if Q is bigger than KSP, we've pushed past the solubility of the salt. Is that okay, y'all? Okay, what else? Are we done? Yeah.
When you get that nice box, it's like you just take the water and you just look at that and split it up into like a square.
Yeah.
And you get that nice box.
Yeah, good question. And so the answer is, whenever you're solving for KSP, can you see that in your head? So in order to solve for KSP, you need the molarities. So if you're solving for KSP, they have to give you the molarities, and those just plug in. So then the question is, when do you need to icebox? And the answer is if you're solving for equilibrium molarities, right? So for example, if we had, come on, let me move. I know it. And so, oh, that's a minus. So if the question, I got to get this out of the way. So if the question was something like, hey, what is the molar solubility of calcium fluoride? So we would go, there's none of this, there's none of this, there's none of this. This is plus X, this is plus 2X. So then KSP is equal to Ca2 plus wow, this is a mess, and 2 fluoride and square, and then we plug this in, and this would be x, and this would be 2x squared, and then off you go. And you solve for x, and then that would give you the molarities when it's, so that's when you need to icebox. So when you're solving for equilibrium conditions, you need to icebox. If you're solving for KSP, they'll give you equilibrium conditions, and then you just plug it in. What else, y'all? Good? Okay, let's pause. Let's get this recorded. And then, guys, you need starting this and grabbing this. Okay. All right. So, guys, John will be back. I'll just drop in the paper. So, guys, today is the last day of this unit. We agreed together that we were going to take the test. We're going to take the test on Tuesday, which then buys us Thursday to start on electrochem. But, guys, oh, it's frozen. There we go. So guys, today what we're going to do to wrap up this unit is we're going to talk about titrating weak acids and bases. So guys, this is my summary of what these calculations look like. Guys, don't let this cause more confusion than benefit. I've had some people that over the years have looked at this and said, oh, now I get it. I've had other people look at this and go, what on earth does this mean? So guys, if this helps, great. If it doesn't, please just pretend you've never seen this. But if nothing else, what I'd like to do is this. I'd like to drop them on the floor. All right. So, guys, what I'd like to do, especially because we did not get to lab last time, what I want to do with you, and maybe this would be great review and you choose to write it down with me. Guys, what I'd like to do is I'd like to start the day by remembering what we learned last time in second period. No, 2 times ago in second period about titration curves. So, up to you, but this might be worth writing down. So guys, titration curve looks like so. Whether you're writing this down or not, what goes on the y-axis? Nope. pH. Down here goes volume of what? Don't say sodium hydroxide. Not even the base, the standard. Then guys, let's set this in a strong environment. Is it okay if I just use HCl and sodium hydroxide and then acetic acid? Never mind, we're going to do that. It just allows us to not think, oh my gosh, is potassium hydroxide a strong base? So let's go with familiar. Again, guys, this isn't new. We're building foundation for what we're up to today. Then, guys, let's say that this is a 0.1 molar sodium hydroxide solution, and let's say this is a 0.1 molar HCl solution, again, using numbers that work out pretty. Then let's label 7, let's label 0, let's label big. And then guys, whether you're doing this or not, either mentally sketch on my screen or physically if you're doing it on your own, sketch the titration curve for this titration. They'll have you do this on the test, maybe, but it's not off limits. Sketch the titration curve. Guys, when you do this, and again, there's no guarantees on the AP test, but when this has been on the AP test, they specifically said, label, if you will, where the curve starts, where the curve goes vertical, where the equivalence point is. Oh, one other bit of information. 25 milliliters of HCl. So guys, now that I'm realizing this, as I'm thinking about this, I know I said, do it if you want. Maybe you should have, if you're not, but you can probably do it in your head. So guys, again, where did it start? You need to label that point. Where does it go vertical? And what is equivalence? The pH of equivalence. You guys done? So let's talk. So guys, where does the graph start? pH of 1. How do I know that? Negative log of 0.1. So guys, the molarity is 0.1 molar, and as a result, this is a strong acid. It completely dissociates, so the pH is the negative log of 0.1. Yes? Okay. Read the box in the upper left-hand corner of the paper that I gave you. So, what is the pH of a strong acid-base titration? It's equal to the negative log of the concentration of the original solution. I didn't put in the negative log because I assume that that's clear. But guys, if you want to scratch it in, you can. So in a strong acid-base titration, the initial pH is given by the negative log of the initial concentration of the acid. Is that okay? Okay. Then guys, from there, wow. We're having a little disco party up here. So guys, now let's label this 25 milliliters. Why is 25 milliliters important? That's the point of equivalence. But guys, check this out. They love to do this to you on the test. That is not always the point of equivalence. What is it that makes it the point of equivalence in this example? The molarity of this and the molarity of that are the same. So guys, what if they weren't the same? How do you find the volume of equivalence? You actually have to do it using dimensional analysis. You start with the, well here, can I just show you quick? What you would do, what you would do is you would go, there we go, 25, so imagine that it was a 0.2 molar base solution. You would go 25 milliliters of HCl, 1,000 milliliters is 1 liter, 1 liter of HCl is 1 liter is 1 mole, that's HCl, is 1 mole of HCl. So liters, moles, 0.1 mole. Yeah, so we're 0.1 moles of HCl. Then guys, for every 1 mole of HCl, wait, how do we do this? Yeah, so we're in moles of HCl, but we need to be in moles of NaOH. Yeah, 1 mole of HCl is 1 mole of NaOH, and then 0.2 moles of NaOH, holy smokes, is 1 liter, and then 1 liter is 1,000 milliliters. Wow! So that's how you find the equivalence point. But guys, functionally, what does this work out to? Well, the thousands cancel, and so it's really just 25 times 0.1 divided by 0.2. But that's how that math works out if you need to find the equivalence point. Is that okay? Yeah. Yep. You guys okay? All right. So functionally it works out to 50, right? No, 12.5. Because if the base is twice as strong, you need half as much. All right. So guys, moving along then, because these are equal, we know that our equivalence point is going to be at 25, so we move up steadily, then we go vertical at 25, then we peel off. Guys, they won't ask you where it goes, like they won't ask you to identify these points, but you do need to identify that point. Why is it pH 7 in this case? Yeah, because these are worthless, right? They're the children of strong acids and bases. So the equivalence point would be at 7. And then guys, so long as we're talking about this, we know how to find the pH initially. We know how to find the pH at equivalence because, as you said, strong acid base, right? So it's going to be 7. Then guys, just really quickly in your brains, how do we find the pH before or after equivalence? Remember what we do is we convert to moles and then we subtract to find out what we have left over, and then we convert that to a molarity, and then we take the pH or the PaOH from there. Remember that? Okay, so guys, with that said, does this whole top horizontal row make sense? So initially, you're just taking the negative log of the concentration of, in this case, the strong acid. Before equivalence, it's equal to the concentration of the unreacted ion. This is found by subtracting. Remember to convert to molarity, which means the volumes are additive. And then you'll notice that what is before and what is after equivalence is exactly the same. So guys, even if these words would not have been your words, do you understand the idea? Are we okay? Good? Questions or thoughts? You're all right? Okay. So now, guys, what we need to do, and I'm going to encourage you to sort of draw this, but let's do it in a quality, if you will, way. Guys, now what we need to do is we need to look at where we started. This is what we just drew, right? And guys, bringing in the terminology, we know the equivalence point is where we have equal numbers of moles. But guys, what do we call the points where these things change colors? They're called endpoints. We call them endpoints because that's where you end the titration. But remember the idea, guys, that your endpoints and your this is important. You'll see it on the test. Your endpoints and your equivalence points do not need to be the same, so long as the endpoint falls somewhere on the vertical portion of the titration curve. Yo? Okay. So now, guys, let's do this. Let's fly in a weak titration. Before we draw anything, guys, let's sort of zoom into this and let's talk. So now what we've got is this. We still have our original titration curve in blue. We're going to say, here, let me be able to write on this. So guys, we've got our original titration in blue. Notice we have sodium hydroxide. Why did it do that? Oh, I clicked off the screen enough that it moved. Sorry, just a second. So, guys, we've still got sodium hydroxide, so that is still our base. This we'll say is HCl, and then this is CH3. This is vinegar. So, comparing these two, let me just give you a minute to sort of sit with this. What catches your eye now that we have superimposed the weak titration curve on top? What are the interesting bits? Let me give you a second to think about it. So guys, similarities and differences, what do you find interesting? Go ahead, Joe. Great. So guys, after, and let's talk about why this is interesting. After equivalence, they superimpose, they're perfectly overlappable. So what's going on? Well, guys, the idea is this. What happens at equivalence? They're equal, right? We've got equal moles, in this case, of base and acid. It doesn't matter if it's a strong acid or a weak acid. Guys, at equivalence, the strong base has kicked butt on any of these acids. Whether it's strong or weak, that sodium hydroxide kicks butt. So guys, at equivalence, regardless of which acid you're talking about, in the beaker, you ain't got no acid left. It's all been converted into product. And so guys, at that point, anything past equivalence is just like dumping base into water. And so those are perfectly superimposable. So guys, do this with me. Grabbing your paper again, and again, only if this isn't misleading, look at the bottom right box. Do you notice that it's the same as the thing above it? Get the idea? So guys, the idea is that when you're past equivalence, in order to find the pH in that region, you just convert to moles, subtract. You're going to have an excess of sodium hydroxide. Convert that to a molarity. What's left over, convert it to a molarity and take the POH. Is that okay? Okay, what else do you notice, y'all? Other interesting things, Jared.
So if your standard was a weak base,
No. Can I get a hallelujah? We don't have to do that.
but the thing that you like, so like the pure was filled with the weak one and the beta plot was filled with strong one.
Then you're titrating backwards. You always add strong to weak. You never add weak to strong. Yeah, because at that point, you can't study something strong with something weak. This all hinges on the idea that what you're adding, whether to something strong or to something weak, this whole thing hinges on the idea that the thing that you're adding is strong, and therefore it's quantitative chemistry. With that said, you could add weak to weak, not weak to strong. That doesn't do you any good. You could add weak to weak, but then are you doing calc? Okay, so when you add weak to weak, you actually have competing equilibria. You've got an equilibria shifting in equilibria. It's kind of like a related rates problem, and the only way to solve it is with calc. So, yeah, have fun with that your junior year. Yeah, so do you understand the idea though? Okay, so guys, other interesting bits? Yeah. Yeah, let's talk about this. I really wanted Elizabeth to be here to talk about this because she mentioned this before. Actually, what's happening is initially when you add, and we're going to talk about this more after the lab because you're going to see this third period in the lab. What is actually going on is that, I'm going to just draw it. Technically, this should go up like this, but it doesn't because it's buffering itself. Weird, right? So what's going on, Ray? Well, here, I can show you. As we add the base to the acetic acid, what's happening is the base is stealing hydrogen ions off the acid, and it's creating this. But now look at what we've got. We've got a weak electrolyte and its conjugate ion, and it's building its own buffer. And so this is what we call a self-buffering system. We're going to talk more. Don't get all caught up in it. It's an interesting idea. At the end of the day, it's not anything to really get too hung up on. Shoot, I can't erase enough. But we'll talk about it more when your data shows that, and we'll sort of pencil out the chemistry. Yeah. Guys, other interesting things. Yes, I did. I believe. I think I did. Yeah. So guys, you're missing two biggies. Let me ask you this. Would methyl red be an appropriate indicator for the weak titration? No, why not? It's not on the vertical section of the thing. Guys, that's why phenolphthalein is sort of our gold standard, because whether it's a weak or a strong titration, phenolphthalein tends to fall on the vertical portion regardless. But methyl red wouldn't work. Methyl red would actually change colors back here, and you're nowhere near equivalence. Now, guys, the last one. What is the pH at equivalence? Well, so what about maybe what is the pH relative to the pH of equivalence of strong titration? It's higher. So guys, quickly in your notes, would you pencil out the chemistry that explains why? Why is you don't need to do the math, don't do an icebox, qualitatively. Guys, why is the pH higher than 7 at equivalence? Guys, you're going to see this on the test. It's going to be like part B of an 11,000 step free response question where they say, hey, you're titrating a weak acid. Explain why the pH at equivalence is not 7. How would you answer that question? Yeah, Jared, I am recording. How would you answer that question? Can we talk? Do you need another second? Just fine. Hey, how did that go? Oh, thank you. Okay, sounds great. Are you a Caramello candy bar fan? Shoot, because there's one over there. It turns out that our copy center person, that's her favorite candy bar. And so I've been feeding her Caramello bars because she's been making all my AP copies. So, no. Because I made, those copies? I thought you meant my candy bars. No candy bar for you. But yeah, so guys, this is all of the material that eventually you're going to get really familiar with. This is all the stuff for AP review. Told you I'm good at this. All right, so guys, here's the question. In this titration, weak acid, strong base, what is the equivalence pH? Above 7. Why? Guys, what does it fundamentally come down to? Acetate ion. Guys, that's it. We're going to talk about this now. We are going to icebox it in just a couple minutes. But guys, the answer is this. The chemistry that we are looking at, can you read that okay? Or is it sort of being lost into the clutter? Is that okay? So guys, the chemistry that we're looking at is acetic acid reacting with sodium hydroxide. And guys, the products of that are sodium acetate and our good friend water. So then guys, we've got to look at this as a salt, largely because it's a salt. So what do we know about sodium ion? It's the child of the strong base sodium hydroxide. Its reactivity towards water is of negligible strength. But guys, what do we know about acetate ion? Yeah, it's a pretty good weak base. So then guys, let's just do it here. So the idea then is that the acetate ion then does chemistry with water, and when it does, it takes its proton back, and that releases OH, and that OH is where we get the basic solution. Get it? Okay, so guys, that is one of the things that we need to talk about today, but anchor it to this table just to see if this is helpful. Look below the big 7. How do you find the pH at equivalence? It says it is not 7 due to the hydrolysis, the breaking down of water by the resulting salt. It can be calculated using Ka or Kb values for the conjugate ions. So guys, join me at the board for just a second and let's talk about this. When we find the pH at equivalence, we do not icebox this. What we do is we find the conjugate ion that is actually causing the pH to be different than 7, and we icebox that. What's that? Depends on what they give you. So yes, but that's a great point, Michael. If they gave us the Ka for this, we would need Ka times Kb is Kw, because, and that's a great point, what we really need is the Kb for this. Sometimes I'll hand it to you. Sometimes you have to Ka, Kb, Kw. Yeah, great observation. So guys, that is sort of setting the foundation, if you will, for the calculations that we're going to do today. So guys, in summary, here's where we're at. Let me try, are you? Oh, okay. So guys, let's take a look at this and see what we got going on. So here's what we've got to do. Just like we did before. Guys, in a strong titration, the pH before you start is the negative log of the concentration of the strong acid. Then at equivalence, it's 7. Before and after equivalence, we subtract to find, we convert to moles, subtract to find the number of moles of the unreacted ion, convert that to a molarity, take the negative log. That's the strong guys. Guys, when we do the weak guys, we got to figure out the pH here. We got to figure out the pH here. We got to figure out the pH here. And we got to figure out the pH here. So guys, how do we do this? Well, imagine that you have the question. Let's say we've got 0.1 molar acetic acid 3 weeks ago. Guys, how do you find the molarity of 0.1 molar acetic acid? Icebox, right? This is an icebox. Guys, how do you find the pH before equivalence? Think about this. We have got, hear this carefully, we have got a weak electrolyte that is getting its butt kicked by a strong electrolyte. What structure do we have in place to talk about butt kicking and then equilibrium? iRace box. These are iRace boxes. Then guys, how do we find the pH at equivalence? And that is this. We use an ice box, but we ice box what the conjugate ion is doing to the water. Then, how do we find the pH past equivalence? It's exactly the same way that we did with strong acids and bases. Y'all ready to go? Because we're going to do an example of each one of these. You scared? Then let's do it. All right, y'all. Here we go. Bump, bump, bump. So you've got this. Here we go. Guys, calculate the pH of a solution that is formed when... wait a minute. Are these our titrations? Wait, it may be the wrong questions. Please hold. Wait a minute. Wait. Oh, okay. You know what? Let me change the language of this because we're going to see these in more like titration language. So let's do this. 50 milliliters. So 50 milliliters of 0.1 molar this. Hold on. I was afraid of that. Just a minute. I want to do this so that I don't get the subscripting carried forward. Okay, so here we go. 50 milliliters of 0.1 molar is titrated with, here we go. All right, so 50 milliliters of 0.1 molar acetic acid is titrated with 45 milliliters of 0.1 molar NaOH. You know what, I'm going to totally change this up. 0.1 molar NaOH, period. What is the pH? Okay, but now we're going to add another question. A titration begins with 50 milliliters of 0.100 molar acetic acid. What is the initial pH? Here we go. All right. Now we're cooking. Boom. Okay, so guys, you solve this. 50 milliliters of 0.1 molar acetic acid is set up for titration. What is the initial pH? Solve for that. There we go. Now, oops. Then this solution is titrated. Now we're cooking. Okay, then that is it. So good. I should be a teacher. Oh shoot, did I get rid of it? 1.8 times 10 to the negative fifth. I guess really that needs to be up here now, doesn't it? There we go. Yeah, I'm sort of, as you can tell, making this up on the fly. This allows it to transition more cleanly into what we're doing. You know what I'm going to do though? Hey, look at that. So 1, 2, 3. There we go. Oh, so much better. Boom. Oops. Wait. Boom. Okay. That was fun. You guys done? Is it 4.74? Have you guys not got an answer yet? Did anyone get an answer? All right. Make me do all the work. CH3COOH in equilibrium with CH3COO, and protons and icebox and 0.10000, 0.100 minus x plus x plus x, 0.100 minus x, x, and x. Ka is equal to acetate ion, protons, unprotonated acetic acid, 1.8 times 10 to the negative fifth is equal to x squared, and 0.100 minus x, which is approximately equal to x squared divided by 0.100. Oh, you're right, because it's not 1 molar, right? So 1.8 times 10 to the negative fifth times 0.1 and square root. And so, guys, the molarity I get is, I'm just going to scratch it here, 0.0013, and then pH is equal to the negative log of hydrogen ion is equal to the negative log of 0.0013, 0.0013, boom, boom, I get 2.89.
Yeah.
Hey!
Yeah, but you said it was like 7 or something.
You thought it was, oh yeah, I think that's when it's 1 molar. Yeah, because 1.8, because Ka is equal, pH is equal to pKa when it's 1. There's my 4.74. What do you think, y'all? We okay? Yep, so pH is 2.89. Yeah, so what I want to do is I want to put this in context. So, guys, let's talk about what we just figured out. So what we just figured out here, oh, I'm going to do this. This will work better. Okay, so here's what we just figured out. So we did this calculation, and we got 2.89. So guys, looking then at the curve, what we just figured, oh, look at that. We just figured out that point right there. Is that okay? So the idea here is that when we find the initial concentration in a titration like that, all you're doing is iceboxing the initial, in this case, weak acid, when nothing's been added to it. No NaOH. You guys okay? Okay, so now guys, here comes the NaOH. So the next point that we're going to look for is this. We're going to figure out this. Because now, guys, we're going to look at what happens when we then start to titrate this. And I believe the question that I wrote is 45 milliliters. So just eyeballing this, it should fall somewhere around 6. But guys, let's talk about the chemistry before we do the math. So can you picture it? When we're down here being all happy, we've got acetic acid just chilling, doing its equilibrium thing, and we figured out its pH, 2.89. Then we start busting on this thing with sodium hydroxide. And the sodium hydroxide comes in and it beats the bajinkers out of the acetic acid and it converts it into acetate ion. Sounds familiar, right? It's what we did with buffers. The only difference is this is not a buffer. It doesn't have an elevated concentration of acetate ion, but iRace still works. So guys, the question would read something like, it may not let me do this. Oh, it did. Like this. This solution is titrated with 45 milliliters of sodium hydroxide. What is the pH? I really like the way this is flowing now. You just got to see lesson planning on the fly. And guys, if you have suggestions for improvement, let me know. Like, for example, if I may. Thank you. So guys, initially the idea was this. You would have had this, right? Which gives you the context. And then this would be the follow-up question. So here's my question. Because question number 1 is not here anymore, does this question lose its context? Or are we okay? Because it says this solution. Do you remember that solution? Is this appropriate, or should I keep question 1 to give you the context for this solution?
I mean, I remember right now, but I'd rather have it up there like it is.
Okay.
It'd also be nice to see it.
Yeah.
We do have it written above, though.
Yeah, we can keep it. No. About that. Good?
Yeah.
All right. So now, guys, we got to think about the chemistry. So what we've got now is we've got strong butt kicker kicking butt on weak acid. So how do we deal with this? iRace box. So guys, we are iRacing I realize this. Is it distracting that I still write acetic acid like this, but here it's written like that? Are you okay with those being the same? I know, but I just realized, but maybe it's good practice because you can also see acetic acid like this. Anyway. So remember what we do. We'll be all right. We write our conjugate base first because we are iRace people, whether it is a buffer or whether it is just a weak acid. This is the way we handle this. Then guys, we go I, R, skip a space, A, C, E. And then guys, you have the advantage of having a blank, you have more paper. I ain't got more paper. But let's remind ourselves, these calculations have to happen in what units? I know. You're okay. Moles. These are in molarity. So guys, the initial and the reacted part of this is the quantitative butt kicking. That happens in moles. Then the return to equilibrium, the ACE, that happens in molarity. It's an equilibrium. It's a rate. It's a molarity. It's concentration dependent. Okay, so guys, you need to show this work. I will do it. So we need to know how many moles of each. So 50 milliliters. 1,000 milliliters, 1 liter, 0.1 moles, 0.050 moles. Is that true? Hey. And then guys, 45 milliliters. I'm being super sloppy. Of course, some of you are too. This is actually kind of what some of your tests look like.
0, 0. It should be 0, 0.
What? Oh, okay.
It would be really slow.
Really? So this is 0.005. So this would be 0.0045. Is that true? Okay. Thank you. All right. So guys, taking that information then, this would be I'm going to get all fancy and switch colors. 0.00500 moles. Now guys, this is the place where this becomes not like a buffer problem, because we have not added a conjugate-based salt. Then we need to figure out how much of this was reacted. But guys, we got to figure out the chemistry. Seriously, spend the time to do this. If we are adding OH, does that move the equilibrium to the right or to the left? Yeah, so guys, just watch charges. This is negative. Does negative attack negative? No, negative attacks this. So this moves the equilibrium in this direction. We know that a side product is water, but that doesn't matter. But guys, what it does mean is this. The amount of this is going down. By how much? The amount of base that we're adding. And this goes up. How much? By the amount of base that we're adding, and this doesn't change. So this then, guys, is 0.00050 moles, and this is 0.00450 moles, and this is still 0. So now what do we do?
Divide by 20, because it's 15 plus 45.
Good. Yep, there you go. So guys, now we convert to molarity. And we do that by dividing by the additive volume. So 40 and 55, did I do that right? 0.095 liters. 95 milliliters, yeah. All right, so we've got 0.0005 divided by 0.095. So let's go two significant digits. 0.005. Actually, we get three significant digits. 26 molar. And then 0.0045 divided by 0.095. We get 0.0474 molar, and still 0. We doing okay? Now it's just an icebox, y'all. Minus X, plus X, yep, plus X. So this would be 0.00526 minus X. This would be 0.0474 plus X, and that's X. Then guys, I'm going to take some liberties with the Ka value, the Ka expression, but I don't want to do it down here because we don't have space. You guys are going to need to feed me these numbers. But we're going to go Ka is equal to then 1.8 times 10 to the negative fifth. What was my acetate ion concentration? 0.0474?
Yeah.
Is that a coincidence that it's the same as... That's a coincidence.
Yeah.
That would be plus X and X. And then 0.00, what was this?
526.
Thank you. And that's minus X. So then, guys, you remember the special sauce. The plus X and the minus X go away. So this is approximately equal to 0.0474X divided by 0.00526. So 1.8 times 10 to the negative fifth times 0.00526 divided by 0.0474, and then That is X, right? Yeah, so let me put this in scientific notation. I get 2.00 times 10 to the negative 6th. And then we go pH is equal to the negative log. I should write this out, but I'm just going to do this. So inverse log. And guys, I get 5.7. Is that okay? Okay, so guys, with that done, are we done? Are we okay? So guys, with that done, let's compare. To the accuracy of a graph that was never meant to be quantitative in nature. So we've got maybe 45. You get the idea. But if we bring that up, well, it's probably more over here. But it's within the range of possibilities given that this wasn't really plotted with data. Do you get that process? Okay, guys, we got one more to do. This is the winger schninger. This is the tricky bit. This is for all the bananas. This is the big kahuna. Yep. So guys, is this okay? Calculate the pH at equivalence. Do we have enough context for us to understand that we are equal? We're equal volumes because we're equal molarities. Is that okay? Or would it be helpful to have the previous two questions for context? You guys are the students. I already know how to do this. Are you okay if we just do this? Let me do this. Let me get into it with you. And then if you find yourself going, no, it would have been nice, I can go back and add it later. So guys, how do you handle this? How do you answer this question? What is that pH? And guys, the answer is you look at two separate reactions. The first reaction is the reaction between the acetic acid and the sodium acetate. Or I'm sorry, the first reaction is between the acetic acid and the sodium hydroxide. Then once you've done that, you can use that as a guide that will then lead you to the chemistry that dictates that point. So guys, how do you do this? I'm glad you asked. Here we go. So guys, doing this with me, we first of all have got to write down the overall chemistry. So we've got CH3, COOH, plus sodium hydroxide, and that yields, let's just do it this way, sodium acetate and water. Do you want to draw a beaker or can we picture it? Okay. So guys, let's do this. We're going to draw a beaker. What is in the beaker? When we're at equivalence, what is in the beaker? So we got water, because that's a product. What else is it? How much acetic acid is in the beaker? None. It's all gone. How do we know? Because we're at equivalence, and that's what equivalence means. So guys, that's gone. How much sodium hydroxide is in solution? Also none. This is gone. Where did it go? Turned into sodium acetate and water. So guys, when we're at equivalence, what we've got in that beaker is sodium acetate and water. Now, sodium acetate, does it completely dissociate? Does it break apart? Does it ionize? Sure, yeah, sodium's all acetate, gone. So guys, what we've really got is sodium ion, and we've got acetate ion. But of these two, which one mucks around with water? Yeah, not the sodium. So guys, fundamentally, what we've got is acetate. So the chemistry at equivalence has nothing to do with this chemistry, because you ain't got none of that no more. So guys, the chemistry that is of importance is the chemistry of the acetate ion, because that's what's attacking the water. Go ahead. Correct, but the tricky bit is, well, and we should be careful. Well, no, we don't need to be careful, because we understand that we've got acetate ion, right? This and this is full bore gone. It's turned into water, right? So that's off the table. So we do have some sodium ion, but that sodium ion doesn't do any chemistry with the water. But I like what you're thinking. You're like, wait, that's a weak electrolyte, isn't it? It doesn't go back. What it does is it attacks the water, and instead of going back to our, because remember, this is not equilibrium. This goes and doesn't go back. The thing that does go back is this chemistry, and that's what we're about to icebox. Okay? But guys, here's the question. And so let me write that out. But I don't want to lose my space. So guys, the chemistry that we are going to icebox is the acetate attacking the water. Okay? But in order to do this, we're going to icebox this. But guys, in order to icebox this, what kind of values satisfy an icebox? Moles or molarities? Molarities. But guys, we need to know the molarity. So let's look at what we've got. Let me clean up this mess. So guys, we've got CH3COOH plus NaOH, and that forms sodium acetate and water. That shouldn't be there. Okay, so guys, how on stinking earth do we figure out the molarity of the acetate ion? Now it should be there. Bingo. Or this, right? Yeah. So guys, the number of moles of this will be equal to the number of moles of this or the number of moles of this. Why are these the same? We're at equivalence. So guys, the number of moles of acetate that come out is equal to the number of moles of either one of these that went in, because they're equal, because we're at equivalence. So all we got to do is do the math. So we've got 50 milliliters of the acetic acid, 1,000 milliliters, 1 liter, 0.1 moles. We've already decided, is that 0.005?
Yeah.
Okay, so 0.005 moles of CH3COOH, or 0.05 moles of NaOH. Those are the same. But guys, this number of moles is the same as the number of moles of acetate ion that got created through the butt kicking, right? So how do we then convert that into a molarity? Divide by the volume. What is the volume? What is the volume of the solution? Yeah, 50 milliliters of acid, 50 milliliters of base. So guys, this molarity is equal to moles divided by liters, 0.005 moles, 0.1 liters, because it's 100 milliliters. So that would be 0.05 molar. Is that okay? All right, let's icebox it. Here we go. CH3, COOH, no. CH3, COO minus, plus Wawa in equilibrium with CH3, COOH plus hydroxide. Guys, was that too much too fast? Do you see what we're doing? If you're not sure, guys, let's go back for just a second. So this is what we've said. We've said that when we're at equivalence, all of these are gone. And when we're at equivalence, sodium doesn't do chemistry with water. So when we're at equivalence, this is the chemistry that we're looking at. Acetate ion attacking water. That is this. Acetate ion attacking water. Again, in order to satisfy the ice box, we know that water does not have a molarity. So what we need to know is we need to know the initial molarity of the acetate ion. That's this. The number of moles of acetate ion that are created are equal to the number of moles of either one of the reactant that went in. So this would be 0.005, then converted to molarity, we divided by 0.1 liters, because that's 100 milliliters, the total of the solutions. Questions there? Okay, then let's icebox this. So we've got, 0.05? Okay, so 0.05, 0, 0, minus x, plus x, plus x. So 0.05 minus x, and x, and x. So then KB is equal to, oh, Michael, here was your thought. We're going to have to do it. Good for you. So KB is CH3, COOH. We're going to just finish this up, y'all. And OH. And CH3, COO minus. And so then we've got, I'm going to just do it down here. Guys, remember we've got the Ka of acetic acid. If we need the Kb of acetate ion, Kw is equal to Ka times Kb. Kw is 1 times 10 to the negative 4th is equal to 1.8 times 10 to the negative 5th times Kb. Have you already done the math? No?
14.
Oh. That's better. 1 times 10 to the negative 4th times divided by 1.8 times 10 to the negative 5th. 5.6 times 10 to the negative 10th? Yeah?
Yeah.
Good. So 5.6 times 10 to the negative 10th is equal to x squared all over 0.05 minus x, approximately equal to this. So we have 5.6 times 10 to the negative 10th times 0.05, take the square root, and I get 5.3 times 10 to the negative 6th. But guys, remember, that is not a hydrogen concentration, that's a hydroxide concentration. So guys, what I'm about to do is completely inappropriate, but I just want it to fit. So we're going to take the negative log of that, and I get 5.3. Really? Yeah. So guys, hey, POH is equal to 5.3, then pH plus POH is equal to 14. So subtracting that from 14, guys, I get a pH of 8.7, understanding that I way cut too many corners. So 8.7, did you guys come up with that? Let's check. Again, this isn't a great representation, but we get, it's not great, but that should be 8.7. You guys okay? Go ahead. Or are you just covering up? You okay? Yeah. Yeah, good question. And so here, let me go back to the calculation. So the idea is that in the previous two questions, we had been mucking around with acetic acid. And they gave us the they gave us the Ka for acetic acid, which is 1.8 times 10 to the negative fifth. The problem is that in order to solve this question, we need to know the Kb of acetic acid's conjugate base. And so in order to do that, and this is straight off of our AP equation sheets, we've got this statement that says Ka times Kb is Kw, and Kw is 1 times 10 to the negative 14th. So this expression allows us to convert. Is that okay? All right, so guys, 2 more seconds. Let me just ask. So the last thing we need to do then is talk about this. So guys, it will not let me switch, so hold on a moment. So this then, so now past equivalence. So gang, up in this zone, this is just the same thing as with a strong acid base. You just figure out the moles of acid, figure out the moles of base, subtract. In this case, the moles of base will be greater. So you'll convert that to a molarity, take the negative log, that gives you POH, and then you convert to pH. Is that sitting okay? You good? Okay. So guys, homework. Looks like this. I'm going to stop recording.